Do you feel like you've watched lots of videos and read lots of things about SVM, but you still don't fully understand this algorithm? If the answer is yes, then this video is for you. But even if you start from scratch, you should also stick around. SVM is a classification algorithm, but you can also use it for regression. You have two or more classes and you want to separate them using a linear decision boundary. In this example, in a 2D space, there are many lines, actually infinite number of lines that can separate the classes. But which decision boundary, or a hyperplane as we call it, is the best one? Many people call SVM as a maximum margin classifier because it uses a decision boundary and margins to separate the classes. In this example, it looks like the dashed line is equidistantly away from both classes. So how does SVM come up with this decision boundary? To answer this question, we first need to remind ourselves of the dot product, the pillar of the SVM algorithm. Let's say we have a vector x and a vector w. We are projecting the vector x onto the vector w, and this order plays a role in SVM, so keep that in mind. This dot product is a scalar, and it is the length of the projection of vector x onto vector w times the length of the vector w. Let's check a special case of dot product, where the two vectors are perpendicular to each other. In that case, their dot product is 0. Let's also assume that w is a unit vector, and for now it's fixed, so it sits there in its two-dimensional space nice and calm. Let's now write the dot product of w and x. Here we are just expanding that dot product and bringing x2 to the left, so this new form reminds us of the known equation of a line. So this dot product represents a relationship between x and w in the form of an equation of a line. All these vectors x1 and x2 that form a 90 degrees angle with the vector w fall into this line. What if we move the line to the right, keeping the angle the same? Well, that's easy. We just simply add that intercept to this equation of a line. Okay, we can rewrite this equation to look like an equation of a hyperplane. Alright, in the context of SVM, you might have seen this equation also written like this. We will see in a while what that b, or minus z times w2 from above really means geometrically. We call that an equation of a hyperplane. Interesting and important thing to notice is that the vector w, which is a perpendicular vector to the hyperplane, is embedded in the equation of the hyperplane. Hyperplane is one dimension less than its ambient space. In our example of 2D space, a hyperplane will be a one-dimensional flat space, in other words, a line. In a 3D space, a hyperplane is a plane, and so on. If you ask me, I would have named it a hypoplane for that reason. Hyper in Greek means above, whereas hypo, below. Anyway, let's move on to a crucial point. Let's extend the vector w so it touches our hyperplane at some point. Let's say that when we extend it by lambda, the vector w touches the hyperplane. Remember that the length of the vector w is 1. So there is a point on the hyperplane, lambda times w1, lambda times w2, that will fall onto the hyperplane, and it's also an extension of the vector w. Let's plug those numbers into our equation of the hyperplane. Here it is. Let's do some simple calculations. Since w is a unit vector, w1 squared and w2 squared equals 1. At the end we get that lambda, or b, or a bias as some say, is the perpendicular distance from the origin to the hyperplane. Alright. Let's use the compact way of writing the hyperplane. Now we finally know what that b is. It is the perpendicular distance from the origin to our hyperplane. Now let's go back to our classification problem. Let's assume that the hyperplane becomes a decision boundary. We want to find a way to tell on which side of the decision boundary our point that we want to classify is. Here is a way of deciding on which side of the decision boundary our point is using an algorithm. Let's first assume that we have a point on the right side of this particular hyperplane. Let's calculate the dot product of w and x prime. We've said earlier that in our case, because w is a unit vector, The dot product is simply the length of the projection x onto W. This dot product is clearly bigger than B, and so will all the points above the hyperplane. If a point falls onto the hyperplane, the dot product will be equal to B. And if we move B to the left, we get something that is familiar to us already. Isn't the thing on the left the same as the equation of a hyperplane we defined earlier? Sure it is. What if the point is below the hyperplane? Let's calculate the dot product again. This time it is clearly smaller than B. Let's repeat the same step as earlier, moving B to the left. Okay, here are shown both scenarios of points above and below the hyperplane. Can we somehow combine the two inequalities into a single relation so we can have an even more comprehensive algorithm? Sure we can. Here is how we do it. You can see that the equations are the same aside from the inequalities. What we can do to create a single equation is to add y in front of the equation of the hyperplane and say that this new relation should be always greater or equal to 0. Y are class labels for points in our dataset. Points that belong to one class correspond to +1, and points that belong to the other class correspond to -1. Let's confirm that this indeed works. Let's say we have a point that belongs to +1 and lies above the hyperplane. The dot product of this point is greater than B, so the relation inside the parenthesis is going to be positive. Y corresponding to that point is also positive, so our new inequality stands for points above the hyperplane. Now try to show that the relation to the left will be also positive for some point that lies below the hyperplane. We've said earlier that SVM is a maximum margin classifier. Aside from the hyperplane line, it comes with two other lines equidistant from the line in the middle. Maximum margin means maximum distance m of those two lines to the line in the middle. First, let's talk about the hard margins. To expand what we have already done is to simply add and subtract distance m to and from the distance b, so we can get those two extra lines. We also want m to be maximum while preserving all the correct classifications. Here we combine those two equations into one after doing some very simple math, and add the y again in front. Shall we check that this new equation works? If the point is correctly classified, then the left part of the equation will be greater than m. Let's confirm. So this part of the equation corresponds to this distance, which is clearly bigger than m. By now I'm sure you can show the same for a point below the hyperplane. Let's talk about the soft margin classifier, because this is actually what most people are using. And the reason is that it can deal with outliers and give some slack to the model. Let's say the pink point, which belongs to group +1, should stay there without moving the classification lines. But if we run the model with hard margins, it will give an error when classifying this point, and the model will try to fix it by adjusting the lines accordingly. Let's see. This time the dot product of W and X is smaller than M, which means that the point would be misclassified because the entire thing is smaller than M rather than greater. Okay, how can we account for that one point so it's not misclassified? In other words, how could we add some slack to the model? We are going to slightly modify the equation of the hyperplane to add some slack to the model. We subtract the slack parameter epsilon from m, so the equation of the line is still valid for that particular point. So in this case, m minus epsilon will be smaller than the length of this little green line, and the point won't be misclassified anymore. But for this to hold, the slack parameters need to be non-negative numbers. Remember that the objective here is to maximize the m, which makes the position of the decision boundary as far as possible from the two classes. The constraint is that w is a unit vector, as we have stressed out earlier. Okay, one last thing is this parameter c, which specifies how big and how many non-negative slack parameters are allowed. It is a regularization parameter. When c is big, the margins become very wide, which means more epsilons are allowed and more points end up on the wrong side. If C is very small, the margins are small and more points are on the right side, but this might not generalize well with new data. Okay, just to wrap up, optimization problem chooses B and W's to maximize M. This is exactly the definition of the maximal margin hyperplane. This problem can be solved efficiently, but the details of this optimization problem are outside of the scope of this video. This is really the last thing. What if the data is not linearly separable, like in this example to the left? SVM is a linear classifier, meaning that the hyperplanes it infers are linear. One extension to SVM called Kernel method deals with these scenarios. Kernel method adds column to the original data, where the new columns are transformed data from the original input. The kernel 5, for example, takes the input A and B, raises them to the power of 2 and adds them, creating a third dimension, seen on the right. Points from the original 2D space that were falling into the circle remain lower in the third dimension than the points outside the circle. Here we can find a linear hyperplane that separates the data. Okay, that was it. I hope you enjoyed this video.